É o Thiago Saraiva.
Santiago Saraiva.
É isso, é da...
Sí, sí, sí está. Santiago Saraiva, sí está, sí está. Perfecto. Ok, todo tuyo, Isaías.
Okay.
Bem-vindo, Mauro.
Okay, well, thank you.
Welcome, everybody. I'm pleasure to present Professor Mauro Dória, professor from Federal University of Rio de Janeiro.
Opa, pessoal. Boa tarde.
Good
Bom
morning,
dia.
Thiago. Mauro changed the title of his seminar, but today he will talk for us possible shape resonance in superconducting nickel bismuth bilinear. Well, Mauro is professor from this Federal University in Rio de Janeiro. Mauro have oriented several students in Brazil and abroad, specifically in Camerino, Italy, and Antwerp, Belgium. And he is a very expert in superconductivity and others field of physics. Mauro, you have 50 minutes to talk, and as I told you, 20 minutes to go. I will let you know. Mauro, with you.
Okay, thank you very much for this nice invitation. I'm very happy to be here. And I think the organizers, especially of all members of LAFMAT for the presence. I thank Isaías for organizing this meeting. And I decided to change the subject because I think that this is more suitable for the community here. So I'm going to talk about some work I have done in the last 2 years to 3 years about nickel bismuth bilayers and possible shape resonances there. So I hope I can bring to you a few concepts that are used in this work that are of general interest, in my opinion. So, okay, let's move on. See. My collaborators are Liu, Yutao, other members of Elisa's laboratory, Professor Litterst from Braunschweig, and we had 2 publications on this topic that you can consult for further details. Okay, let me go to the introduction. This Yutao gave a talk about this subject already, but anyway, it's nice if I repeat some of the basic ideas. Is if you take crystalline bismuth and nickel, they are not superconducting down to 0.5 millikelvin. In fact, crystalline bismuth was shown to be superconductor. I think it was in 2017, say 6-7 years ago. Okay, before it was even not considered to be superconducting. But bismuth is a very interesting and complicated element because amorphous bismuth can be superconductor. And there are always stories about bismuth being a room temperature and having a very high temperature, but this is usually amorphous bismuth that is a mystic word. Okay, in nickel is magnetic, it's not superconducting. And nevertheless, it was found that if you deposit nickel on bismuth or vice versa, this bilayer becomes superconductor. So there were many ideas about this system because people first thought, wow, this is the example of magnetic fluctuations in nickel, which is magnetic, that creates superconductivity. Or perhaps formation of amorphous bismuth, okay? But at the end, what was found is that when you put these two elements together, you make two intermetallic alloys, which is nickel bismuth and nickel bismuth 3, which have critical temperature of 4 Kelvin. Okay, so when they interdiffuse one into the other, you form these two elements, and so that's the answer to the problem. And this was found by Utah and collaborators. Okay, they did very nice high resolution transmission and scanning transmission electron microscopy, okay, X-ray spectroscopy analysis. And by 2018, they verified that there are new elements in this interface. So I recommend the reading of some of these papers here. Okay, what I am going to do here is to mix this, the idea of this new elements, this new superconductor, with a concept that maybe few of you know about it, which is so-called shape resonances, okay, which is a concept that was formulated back in 1963, very long ago, okay? And this concept is the following, that if you take a very thin film and you change the thickness of the film, here you can see thickness of a slab. If you change the size, the critical temperature of the film oscillates like this, has maxima and minima, okay? This is a theoretical work, okay, not experimental. And it was proposed that this would be true in thin films, observable, 1963, very amazing and interesting that such a long time ago, people did this very beautiful and nice speculation, is so-called Thomson and Blatt paper, okay? And so through the decades, people try to find out this effect, okay? And this was claimed to have been found by Kim and collaborators in 2009 in lead films, okay? So here you see the temperature versus the thickness according to the number of layers, okay, the monolayers. And you see that for 2 monolayers, you have nothing. But then if you go from 4 to 15, you begin to observe an oscillation in TC, okay, which is just enhanced. Here is a small effect. Temperature goes from 635 to 610. It's a small oscillation, okay? And was said, well, okay, finally this effect was discovered. Now there are many doubts about this work because nobody was ever able to reproduce it. So it's not true, it's not clear if it is correct or not, okay? It's an irreproducible result. But the shape resonances, so-called shape resonances, they were seen in other systems for sure. For instance, one is thin nanoparticles, okay, that you deposit here or lead into some surface, and then you have nanoparticles. It's not a film, okay, and you go and look at measure the gap, okay, in each particle, and you see that there is an oscillation in the gap, okay, according to the particle size. So again, is a correlation between length and critical temperature, because the gap is critical temperature in some way, okay? So here is measured the particle height for 2 cases of lead and also for tin, okay? And the effect is observed, okay, according to the height of the system, we are in the nanometer range, okay? So the problem is that to observe these shape resonances, okay, you have to consider two special limits in your system that I call quantum size limit and classical size limit, okay? Because as we are going to see, I mean, what's special about the films is that the energy levels are spaced in a different way as compared to the bulk, okay? You have some discreteness of the energy levels, okay? It's like electrons in a box, okay? You have some spacing between the levels. And for this spacing to be noticeable, you have to have that, say, the Fermi wavelength that defines the Fermi energy have to be compared to the size of the system, okay? Otherwise, you don't see this discreteness. We're going to study some, I'll comment some more about the quantum size limit. But there is also the classical size limit, which means the following. You may have a very small particle, but if your electron, for instance, let's take a thin film, I mean, the energy levels are the ones like, I mean, a string, no? Okay, we have that discreteness of the string, you have the very spaced energy levels. However, if the electron, when it goes from one side of the film to the other, it suffers many collisions, okay? Then all this structure is destroyed and you don't see it. So you have to have that the mean free path has to be larger than the size of the system, such that you don't have collisions happening in between, okay? So that's the two systems. For instance, this is a work, I don't refer here the name of the paper, it's a paper by people in Cameroon, as a matter of fact, and theoretical collaborators. And you want to know, for instance, how is the mean free path compared to the thickness. And you see here is niobium. And here's the resistivity, 9 nanometers, 1380, and you see that the resistivity, okay, the critical temperature goes up, okay? So 9 is here, 80 is here, and so is this resistivity here, okay? You see that the resistivity decreases. And it turns out that of course, the thickness, you know it by construction of the experimental construction, you know the thickness. You want to know what's the mean free path of such systems, okay? And how do you obtain the mean free path? Is the same because since it's niobium, it's the same? No, it's not the same. The mean free path varies according to the thickness of the film, okay? And how is it computed, the mean free path? This is an interesting thing, observation. You can use Druid's model, okay? You take the bulk, and if you compute, I will describe this some more, the resistivity times the mean free path, this is a constant, okay? That's a constant. It's a number that's a constant, depends only on the density of electrons, okay, and the mass of the carriers. So using this formula here, you can do the following. You take this resistivity here, which is the less normal state resistivity, and you compute the mean free path here using this value. You can compute it here. And so you can make a plot of the size of the width of the mean free path in nanometers with the the D, which is the thickness of the film, versus the mean free path. Okay, so it's an interesting thing. That you can make an assumption and obtain the mean free path. And what you find out is that when your film decreases in size, so it does the mean free path. But the mean free path, you see, it's always larger than the thickness. Okay, so for instance, here we are in this is 2, this is 1, okay, and this is the thickness is 7, 8, and so it is yeah, it decreases with mean free path, and the thickness is 100, and the mean free path here is 10. Okay, it is similar. Okay, right. So this is what we have here. So this is we can also know the critical temperature, but you can get this experimental curve out of this expression. Okay, let's move forward. Now, a little bit of bismuth, because we are going to consider bismuth and nickel. First, as I told you, Prakash, this was discovered in India, okay? The critical temperature of bismuth is 0.53 millikelvin. It has a Fermi surface of 25 millielectron volts. The Fermi length you can obtain from here, okay, is 40 nanometers. It's say 80 times larger than niobium, which has a very small mean free path. Okay, the Debye energy, which is the frequency of the phonons, you can also discover. So what you find out is that the ratio between the Debye frequency energy and the Fermi energy is 0.5. Okay, so you see that this is not a BCS superconductor, because when we do BCS theory, we assume that the Debye frequency is much smaller than the Fermi energy. So there is something strange in bismuth. Moreover, and very interesting, this is something that is an information, side information of this seminar, is that the mean free path of bismuth is of order of micron, whereas niobium is 30 nanometers. So it's much larger for bismuth, okay? And okay, then you can do assumptions about measure the electron density in bismuth. This has been done in the past. Okay, it's not very large. I mean, niobium is 20,000 larger than bismuth. Okay, so again, I like to emphasize this. These are papers in 1952 by Sondheimer and Piper, which is discovered of the Piper relation of determines the coherence length. Okay, look at Sondheimer. It says it's remarkable, however, that experiments on thin films and wires of bismuth indicate that the free path at room temperature is of order of 10 to the minus 4 centimeters, which is about 20 times larger than the free path in silver. Okay, so in fact they speculate that why the mean free path is so larger. Of course, there are not many collisions with phonons. In here, they says, well, momentum and energy conservation forbid collisions between the electrons and the high energy phonons. This is a way to put things. In my opinion, I like to express my opinion, which is true, but it is an opinion, is that in bismuth, somehow you have the momentum of the carriers associated to the spin in such a way that if you want to flip in collisions momentum, because when you have collisions, that's all collisions are about, you change the momentum of the particles, okay? But in bismuth, this is forbidden, I mean, such a changes, because you have to change also the spin, because the spin and momentum are correlated. That's my opinion, okay? This is what it leads to this high free path. Okay. In fact, if you go and look at Meming and Ashcroft, they use the Druid model, okay, to compute. They take the mass of the resistivity of bismuth, obtain the Druid relaxation time, and so forth, okay, and they obtain the mean free path, okay, out of this, and they are completely wrong. They give values of 10 to the minus 4 micrometers. So this Druid model does not work for bismuth. The information that they provide to bismuth confronts what Sondheim and people says. This is interesting. It's an error in bismuth in Memi. This is what, my opinion, I never found out this comment in any other place. It came from my mind. So if you find that there is something wrong, you please let me know. But if you read off the what they give here for bismuth parameters, you find out that it leads to a wrong mean free path. Okay, so now comes for what Utah View and collaborators did it. Okay, he probably has described this to you. So they have a substrate of silicon bismuth, then they deposit nickel, for instance, and then the nickel, how to say, percolates here, diffuses inside and forms this nickel bismuth, begins to nucleate nickel bismuth, such that the end, what you have is bismuth and a layer of nickel bismuth 3, okay? And what's very interesting about this system from thermodynamical point of view is that you have an initial volume, okay, that you deposit, an initial quantity of bismuth and initial quantity of nickel, okay? And then finally, you have a volume of nickel bismuth 3. Let's ignore the other one. You can have nickel bismuth. I will not discuss this. I'll assume that everything is nickel bismuth 3 because you can, in fact, have the formation of two compounds. Okay. Let's assume that it's just nickel bismuth 3. So I have nickel bismuth 3, and this is for final volume was you have a final leftover of bismuth and perhaps of nickel. Okay. And what you find out is that this final volume here is smaller than the initial volume. So there is some contraction, okay? I mean, this system at room, you have to have under thermodynamic control. I think the position, I don't remember exactly, but it has to be at room temperature. I mean, but at the end, it's something like ice. I mean, when you form ice, you have an expansion, okay, of the volume. We know that. You put water into the freezer, and the water gains volume. Here is just the opposite. You put these compounds, they form this one here, perhaps because of this argument that you have some volume contraction. Okay. All right. So we looked at two systems. For instance, one is initial layer of nickel bismuth, okay? Initial layer of nickel deposited. The nickel basically disappears, okay, and forms nickel bismuth 3, and you are left with a layer of bismuth, okay, some layers. Not in the case that there is not enough, I think it's this 125, that you eat out the bismuth, okay, but there is some nickel left over, okay, so you can have that. But if you have enough bismuth, all the nickel reacts and forms nickel bismuth 3, okay. So the question that I want to address here in this talk is that the final system is superconductor because nickel bismuth 3 is superconductor. Bismuth is not, and nickel is not, but this is superconductor, okay? And here is the case that you have nickel bismuth 3 of the same thickness. So you say, well, my final system has the same TC, okay, because I have this quantity of nickel bismuth 3, but not. You observe some variations of TC, okay, and it seems that the bismuth is affecting the TC of the system. But how come if bismuth is not superconductor? Okay. So what we are here facing is some kind of proximity effect, that you have a super material that is really superconductor next to one that's a semi-metal. So the electrons, they travel to the other side, and somehow this, although not superconductor by source, in its origin, is able to affect the superconducting state. Okay. So this is, for instance, is the case, critical temperature versus thickness for bismuth nickel 3. We have here this nickel 3 case, and you see that if you have very little bismuth, it's not even superconducting. Then if you increase bismuth, you begin to have a TC, and then suddenly when you stabilizes into some layer 25 on, you begin to have a TC near to 4, but not exactly. There are some fluctuations which are expressed here. Okay. So this is the case. This is the case from at least from 30 to 50. Okay, you have no nickel in the final state, and this is the case 30 to 50. You begin to observe some oscillations in TC. So this is what we would like to understand. Okay, we also looked at another system that you have a little bit more complicated. We have deposition of growing layer quantity of bismuth and growing quantity of nickel. Okay, and if the nickel is enough, is sufficient, from 4 nanometers on, we have some oscillations on TC. Okay, so this is from nickel original, nickel 4 up to 16. We begin to observe some oscillations. Okay, and here the TC, here are the oscillations again. You see from this is from nickel thickness from, yes, okay. Okay, this is nickel 3. Okay, this is the one that is concerned here. So that's the problem. Okay. So nickel bismuth 3 per se was studied long ago. There are some very good papers by Fujimori in year 2000, more than nearly 25 years ago. He did obtained lots of information about this material, about the Fermi surface, which is much smaller than niobium, the Fermi energy, a large effective mass, according to him. Critical temperature, very well determined, the gap, the bifrequency. In this case, the bifrequency, the phonons, they have an energy that is much smaller than the Fermi energy. So this is a BCS superconductor. The carrier density is smaller than niobium, but it's okay, 55 to 1.8. The mean free path was determined 20 nanometers and so forth. Okay. So what's the mean free path for niobium bismuth 3? So here's the formula. This is the Druid model formula. If you multiply rho times L, okay, you obtain that this is fundamental resistivity, Q squared over H, a factor here, and then the density here, okay? So it does not depend on temperature, it does not depend on collision. This is a nice number, a nice relation to keep in mind, because if you know the resistivity, you know the mean free path. And then you can compare, here's the ratio between the thickness of the film, okay, and the ratio between L, the mean free path, and the size. And we want this to be much larger than 1, right? We want the mean free path larger than the thickness, so that there are no collisions. Okay, because if you have collisions, you cannot use models like of a string. You know, the electron is like a string, so you want to be much larger than 1. But this is not larger, much larger than 1. It's nearly 1. Okay, especially for we have 2 sets of families of samples. This is the one that's nicer, the red. Okay, you see, it's okay. It's not perfect, but it's okay. Okay, they are okay. This is. I want to go back here and show you. You see here the mean free path is smaller than the density, than the thickness for niobium. So if you have a film of 10 nanometers, we have a mean free path that is smaller than 1. So the electron, when it goes from one side of the film to the other, like a string, you know, like a chord that kids play, okay, that model doesn't work because you have many collisions. The electron has many collisions when it goes from one side to the other. Okay, so here we are. So let's go and do some theory. So the theory that those gentlemen, Thomson and Blatt, did in the 60s is basically Bogoliubov-Desgenais, although they started straight from BCS. But essentially, what's Bogoliubov-Desgenais equations? It's a way to treat superconductivity in real space. BCS is in momentum space. But if you have a film, okay, you have walls in the film. So you have to confine your electrons to some region in space, then you have to use the Bogoliubov-Desgenais equations. Okay, how these equations work, I'll not deduce them, there's no time for this, but what you have is a Hamiltonian here, H0, which is the Schrödinger Hamiltonian with a potential, okay, and this potential will help to confine the electrons inside the film, for instance. And this is the gap. And you have to determine 2 functions, U and V, okay, and determine their energy levels, okay. However, this confining potential, I mean, this structure that you solved has to be done together with this self-consistent equation. This delta is essentially the gap. That's the attractive interaction, and you have these functions U, N, and Vn, okay, that feed into this delta, okay, and then you have to solve everything together with the potential. So you see that it's not simple, okay, but today, I mean, there are many groups that do this numerically in many ways. I do it here in a very pedestrian way that's very useful to understand the problem, which is to use the so-called Anderson approximation. And they discovered the following. Okay, these equations are very complicated to solve. What's the simplest way to do it? Well, I go and solve the Schrödinger equation here, okay? This is a Schrödinger problem, here it is. I obtain the eigenvalues, zeta n, So it's not the true energy levels. And then I claim that U and V are proportional to the Schrödinger states with some constants that I don't know, okay? So when you do this trick, okay, so I'm repeating here the problem just for the film. Okay. I mean, in the case of the film, what is this system? I mean, the U is the potential, okay, and very important. The N, these indices, are the energy levels. In the case of a film, you have two indices. You have one, electrons are free in the parallel direction, but in the perpendicular direction, that's the string, okay? You have a discrete number, pi over 2a. So it's half continuous and half discrete, okay, for the film. And you have to manage to do this, everything together. And here we go back to the Anderson approximation, okay, which I was telling to you, describing to you. This is the Hamiltonian. This is the energy levels. And this is the solution of the Bogoliubov-Dejean equations according to Anderson. Then you feed this into the equations and you find out the Cn and Dn are these constants. Notice, these are the Schrödinger energy levels. And these are the ones that you want to determine. Here they are, okay, which are related to superconductivity. You just can see this expression. And you have many gaps like this, okay? And in fact, you have a potential energy and the electrons into different levels, okay? So, for instance, if you go back to the metallic case, we know we have a ground state like this. In the film, we have excited states, all satisfying this rule, J lambda over 2 is equal to A. A is the thickness, okay? The discrete levels are given by this free particle expression. We feed this into that wavelength, and we find that the energy levels are a discrete number squared, okay, and there is some basic energy. So this is what I was telling you about, how to say, the quantum condition to have observed this phenomenon is that you have to observe this discreteness, okay? But if you take A going to infinity, to the bulk, this disappears. So you have to have the wavelength somehow limited by the geometry. They have to be similar. So you have to have J discrete numbers. So for instance, that's what's interesting. If you take x0 to be 1 nanometer, okay, you compute this number here, and the energy level is 0.38 electron volts. So it's 4 Kelvin, okay? Okay, so that's a connection, Eve to Kelvin. So A equal to 1 nanometers, you have this energy here. So you see for 0.408 Kelvin. If you take a film that has a thickness of 100 nanometers, then this energy, the first energy level, drops a lot, okay? And they begin to approach each other, and you have a continuous...
Pardon, Mauro. You have
yes.
20 minutes.
Okay, so I have to accelerate. So that's the reason why you have those jumps in the temperature, because you have the Fermi energy. This is along the discrete direction. You have the Debye strip, okay? And this is where superconductivity is. And now if you have discrete levels, you begin to have a Fermi surface that crosses some discrete energy levels. And then according to the parameters that you change the thickness of the film, you can have more parabolas under the Fermi surface, under the chemical potential. And that's why you have these jumps in the critical temperature, okay? So this is described in details. I don't have time to go into more information, but you can feel that the size of the system changes the number of parabolas and changes the accessible states in the superconducting strip, okay? And this is what is observed here, Tc times d. Okay, now for the model that we have done for nickel bismuth 3, we looked at a film, okay, with a potential inside here, which describes the bismuth. So electrons in the nickel bismuth 10 to 21, this is 10 to the 18. So we have to make somehow more difficult electrons to go into the bismuth region. So we introduced a potential with a new parameter V0 or Q, keep in mind Q, which measures the height of this barrier here, makes it more difficult to electrons to jump into the bismuth region, okay? And so we go to the Schrödinger equation. Look at here, I have a thickness, which is the size of nickel bismuth. I have a total thickness, and I have a parameter that tells me how height is this barrier near to the Fermi surface. And since this approach, the Anderson approximation, tells me to first solve the Schrödinger equation, you see the Schrödinger equation for here, there are 48 levels. So the more fundamental levels, they are localized inside the nickel bismuth 3. But when they get near to the barrier, you begin to have states, okay, percolate going to the bismuth side, such that for 42 to 43, finally you have a state that's totally localized in bismuth, okay? And then 47, they begin to coexist in two sides, and then you have things even concentrated on bismuth, okay? So this is what we observe, okay? That's another barrier, okay? And we see the same effect. Electrons are initially fundamental level are just in the nickel bismuth 3 side, but then at the end, near to the Fermi energy, they are in both. And that's why the bismuth becomes important in the superconducting state, because electrons can visit near to the barrier. So we take the equations that allows us to compute the gap, and that's what we obtained for these two cases. 0.6 for one potential barrier, a little bit above much below the, not much, but 0.7 of the Fermi surface, in 0.95. You see that the gap, when we do that self-consistent calculation, the gap is mainly on the nickel bismuth 3, but there are some gap living in the bismuth side, okay? That's what we observe, okay? And in fact, if we look at the gap, okay, versus the temperature, we see that the gaps, they disappear, both always, because they are coupled, in the same temperature, okay? But one is much weaker than the other, okay? So then we look at these two systems with their particular thickness and so forth, okay? We want to describe these TC oscillations, okay? And this is what we found in this system with nickel 3 bismuth. This is the critical temperature times the total thickness of the system. We find that it's very sensitive to the height of this barrier. This is a barrier approaching the Fermi surface. And as we vary the thickness, okay, we see that we have many possibilities of critical temperature in this range, not a very large range, but some range. And the best we could do, that's why the paper, the name of the talk is suggestive, because the critical temperature is here, okay? This is the bulk, the dotted line is the bulk. And we see that the oscillations are possible, because this parameter, we don't have it experimentally, okay? It's a possibility. This is the other system that is more complicated here. And we see that according to the height, okay, Q is the height of the barrier, okay, and some parameters that we make assumptions on how much the bismuth is left over, okay, we see that the oscillations follow the trend of the theory, which are these oscillations here, okay, these not the black color, the other color here, okay. Well, so in conclusion, we cannot say, well, that there is TC oscillation for sure. We say that our model is consistent, okay, with the possibility of the old Blatt and Thomson model, okay. Perhaps I went too far because the time is running out. Yes, in this case, we have in this set of samples, we take the point of view, because here we don't know if all the nickel is consumed, okay? But we make the assumption that only part of the bismuth is transformed, okay, according to some parameter lambda, okay? So this lambda sets the thickness of nickel bismuth, and the remainder thickness of bismuth. So there are some assumptions here, okay? But these are our two final plots, figure 7 here of a paper, in figure 8, okay? Which makes us the assumption that, in fact, these resonances may exist. But most important, we are able to explain that why the basic assumption, basic idea is that the gap percolates into the bismuth, okay, and exists here. And this is what influences the critical temperature according to this thickness. Because in principle, only this part is superconducting, okay? This is not. But we claim that this thickness also influences the system. So I think this is all I have to say. Evidence of conclusion, evidence of shape resonances. TC oscillations are observed as a function of the total thickness for various combinations of thickness, and seen both in resistivity and magnetic measurements as well, okay? The remaining bismuth layer goes superconducting by proximity, okay? This nickel bismuth 3 satisfies the classical size limits. I mean, at the edge, say, the mean free path is larger than or similar, in this case, to the thickness of the system. And we observe the volume contraction that favors the onset of nickel bismuth 3. So this is all I had to say to you. Thank you very much for your attention.
Thank you, Mauro, Dória. Thank you very much, and congratulations for your very nice talk. And so now we have some questions from the panelists and the audience. I will, first of all, I would like to do one simple question, talk about the oscillations in the superconducting region and the percolation for another one. And suppose that this second part is not superconductor. This oscillation is because the system is confined. Yes?
Yes.
It remember me the little particle oscillations in temperature. You showed for us, one oscillation of temperature in an old reference. You show very old reference, temperature oscillation in function with the, I don't know why, but it's appear also in the little particle oscillation, and so maybe it has a same similarity. I don't know.
The little particle oscillation requires a magnetic field. So the oscillations are due to the entrance and exit of vortices. Here, you have something that is independent of an applied magnetic field. Okay, it has to do with the thickness.
Yeah, okay, thank you.
The criteria to have such oscillations are the thickness, the electrons, they oscillate, they are in string states.
Yeah, amazing.
If you make the film very thick, this effect disappears, because when you go to the gap, the energy levels are very proximate, near to each other. And what makes it interesting is that you have a discreteness in the levels, okay? And then you have superconductivity in the top one, okay? But you have many of these parabolas that each string state makes one parabola with many electrons in the parallel direction, okay, to feed. So these parabolas, as they enter and exit the Fermi surface, you have more states to participate in superconductivity. That's why you have the oscillations on TC. And the other condition is the one that the electrons, as they bounce from one side to the other of the film, they cannot have many collisions, because the collisions will destroy these states. It will be a mess. So you have these two conditions to be satisfied. Okay, and this is an area that is still unfolding. Okay, there are very new and interesting results by Antonio Bianconi. Okay, you should perhaps invite him for a presentation. That
Maybe.
he makes a multi-layer of superconductors and observe essentially these shape resonances along perpendicular to the what would be the copper oxygen layers. Okay, I mean, as they go this way, they have several thickness to go through. Okay,
Thank you, Mauro. I will invite him here now to make his question. Professor, the more distance invited panelist, the Russian panelist, Tiago Ustrasov. Tiago, are you here? Tiago? Yeah, I suppose Tiago.
Buenos días. Buenos días.
Algo que Tiago no está en este momento, parece que salió un momento.
Yes, because the summer is finishing in Moscow. He has to take
maybe.
some time.
Probably not certainly. Mauro, I have other panelists, but we have here a special panelist invited also. He is a student, André Ornan, who intended to apply to do his PhD in your university, I suppose, in your over your supervisor. So, André Ornan, you have any question for Mauro Dória?
Sí. Yes. Good morning.
Good morning.
Professor. Good morning. Professor Dória, I have a curiosity in the experimental part. In the graph of resistance versus temperature for the phase Bismuth X nickel 3.
Yes.
Could you comment on the separation between size?
Let's see if I get.
Mauro, just a moment. Andrea, if possible, can you open your webcam?
Oh, sorry.
Okay, Mauro.
Okay, you were talking about the. Let's see if I get the experiment. I think is this. I have to share, right? Let's see how do I share. Okay.
Yeah.
Mauro, de paso te comento que André Horna es estudiante de Ángel Bustamante, de la Universidad de San Marcos, que está postulando para hacer pasantía a tu laboratorio.
Sí, yes, okay. Yeah, good. Let's see. I want to share the screen. I don't know how to do. Okay. Okay, I have to share here. Can you share?
Yeah, the 16 or 17.
Yeah. Okay, supposedly I'm sharing it now. I thought I had chosen to share. Okay, well, it's here. I'm asking, are you seeing my presentation? No, no? Are you?
We
Is
can
in stop.
see all slides.
Yeah, sure. Okay, but see.
Yeah. Now you can see. Went. Oh. That's okay.
Oh. Okay, this one. Oh, no, is the
Yeah, now it's okay.
this one.
Yes.
Okay.
In
Would you be so kind to repeat your question?
okay. The graph of the resistance. Okay. Could you comment on the separation between size the 20 and 25? Color red and green.
Okay, the 20 and 25, right?
Yes.
Well, the idea is that from even 25, okay, is not very good. I mean, you see, if you look at can you see my mouse?
Yes,
The
yes,
arrow?
Yes. Yes.
Okay, if you see 25 here, you have a TC. It's much lower than the other ones. This is 4.12, this is 4.18. Okay. And the reason is that in 25, because you deposit 3 nanometers of nickel into 25 of bismuth. And here, all the bismuth is consumed into the formation of this superconducting compound, nickel bismuth 3. Okay, and there is some nickel left. Okay, so we really discard, we throw away this data and begin with 30 nanometers, which in this case we have no nickel left over. Everything is consumed to make nickel bismuth 3. Okay, so you have some final bismuth layer and you have some no nickel left. And here, the first one, we have some nickel left. In fact, I mean, there are things that are not understood here because nickel is magnetic, see? So even what's the effect of nickel into the final compound, because you have magnetism nearby, even if you have nickel bismuth 3, you have some magnetism. It's not clear. When you look at 20, you know, the critical temperature is even much lower here. So this is not even in the table here, not even 15. So we select the data to look at, to see if these oscillations are trying to tell us something or not. Okay, currently we're doing some measurement on nanoparticles, okay, to see such effects. But that's the answer to your question. to the best I can do it.
Thank you, Professor Dória.
Okay, thank
Thank you,
you.
Andrea, and thank you, Mauro, again.
Okay,
Aí, Arturo Martinez. Arturo, are you here? Arturo?
Sí, acá estoy. Eh, ve- excuse me. Thank you for your very nice presentation, Professor Mauro.
thank you.
I have a question. Let me see. You present quantum oscillation for some cases for semimetals and intermetallic materials. My question is, are these quantum oscillations also in oxides, superconductors?
These oscillations, I mean, I think it's this field, I mean, of quantum oscillations. I mean, is something that people worked here and there, and they don't have good consistent results or investigation. Okay, people dropped them in because there is some recent work I can send to you, or you soon will know it about, by people in Italy. They claim that such oscillations, okay, they are responsible for the dome, for the superconducting dome. So when you know high TC superconductors have a dome below which is they are superconducting, is a dome for the TC, right? I'm talking about the diagram T versus doping X. They claim that the dome is due to shape resonances, but not in a single layer. They say that if you have intercalated system of normal superconducting layers, okay, according to depending on the ratio between the two layers, say the normal and the superconducting, you have a dome. Okay, they even claim that this was the origin of the dome. So this is being currently investigated. I think it's a nice area to look at, but they're not consistent. If you screen the literature, you find very little literature, very confusing literature. Okay, because people do experiments, but you have to have these two limits satisfied: the quantum size limit and the classical size limit. These two limits are defined in one of our papers. You can look at them, okay, or even in this talk. I mean, if you want. So it's an open area, in my opinion. Okay, if they have been seen in oxides or not. There are science papers that say yes and others say not.
Okay, I will write my email for the paper.
Okay.
Thank you very much.
If anyone wants a copy of my presentation, just write me an email, okay, and I'll send it over.
Okay, thank you.
Thank you, Arturo. Thank you very much for the question. Mauro, thank you again. Now, who will be done the question is Ximena. Ximena, your time.
Buenos días. Good morning, Professor Isaias. Thank you for your talk. You are an incredible presentation. In this moment, I don't have any question for this, but I want the presentation too, if that is possible, because it's interesting talk. Also, in our university, we don't have question for you. The people only say thank you for the incredible talk. Thank you.
Thank you.
Thank you, Ximena. And I don't know if James, do you have any question, James?
Buenos días con todos. Buenos días, profesor. Buenos días, profesor Mauro. No tenemos preguntas por este lado. Solo felicitaciones por la presentación del profesor Mauro Dória. Gracias.
Okay. Thank you very much, so. And Mauro, if you have any other, your last question, last words for us.
Well, again, I thank you for the invitation. I hope I have contributed to show you of some interesting concepts that live beyond my talk about thin films, new physics of superconductivity in thin films because of these special limits, which is the quantum size limit and the classical size limit that makes the physics different there and are worth of investigation.
Okay, if you for panelists who can open your webcam to thanks again the Professor Mauro Dória. Okay, now
Whoever wants a copy of my paper, please write an email to me, a copy of the presentation.
Okay, thank you, Mauro. Thank you again, and let's take a hand from Mauro Dória.
Okay.
So,
bye-bye.
Okay, thank you very much. And James, you can, just a moment. Luis, you want to say anything?
Well, yeah. Mauro, I was the last question, but quite quickly. In the slide 37, you presented experimental data, right, of the TC with D, right?
Yes.
That is experimental data, and between 3 nanometers to 4 nanometers, there is a lag of experimental data. But what do you expect that happens during that thickness or in that interval of values? Will be also nearly exponential or nearly one big step, or what do you think will happen?
I mean, I don't know. I can give you a guess because I mean, the problem is that when you mix nickel and bismuth, the best is to make all nickel turn into this new compound, nickel bismuth 3, which has smaller volume and it's not magnetic. Because nickel, pure nickel is magnetic. If you have some left nickel around, the question is, what's the magnetism of nickel will do to the superconductor? Probably it will interfere somehow. We don't know. You know, it's an interesting question. It will damage, I don't know. See?
Yeah. Okay.
So I mean, we do work on the simplest possible assumptions and throw on the basket some other considerations because they are very complicated. Okay, what's left? What's done with the nickel that survives this reaction? Okay, so it's a field of open questions, in my opinion.
Yeah, you are right. You are right. Well, Mauro, would you allow me, please, to invite to the public to the second Latin American Conference on Superconductivity and Magnetism? All the public and academics and all researchers are invited to participate in this conference, which will be held in Lima, Peru, and the Faculty of Physics of the University of San Marcos, 23 to 27 October this year, 2023. Everybody can participate. For more information, you can visit all the public who is invited, this can visit the web page of the LAFMAT network. Well, everybody is, I will also invite in Spanish. Toda la comunidad universitaria, el público en general, está invitado a participar en la segunda conferencia latinoamericana en superconductividad y magnetismo que se llevará a cabo en la Facultad de Ciencias Físicas de la Universidad Nacional Mayor de San Marcos del 23 al 27 de octubre de este año, 2023. El evento está siendo financiado por el CONCITEC Prociencia. Además, también mencionarles que están abiertos todavía hasta una semana más los envíos de los resúmenes, de los abstracts. Mayor información en la página web de la red LAFMAT. Okay. Thank you very much, Mauro.
Thank you.
Obrigado, and see you in Lima. Professor Mauro Dória is also going to participate in a conference in Lima. Professor Mauro Dória, if anybody, people can meet Professor Mauro Dória, he's going to give a talk in the conference in Lima in October. Well, thank you very, very much, Mauro Dória. Thank you. Isaías, thank you.
Ciao,
See
ciao.
you. Ciao.
Bye-bye. Ciao.
Hasta luego a
We can
todos.
close.
Bye.
Okay. Bye, bye. Bye.
Bye-bye.
Bye.